Equipment manufacturers and various industry associations carefully monitor lubricant performance to ensure that lubricants meet or exceed all applicable requirements and industry performance standards. To meet these various criteria, lubricant formulators blend specific additive packages with the base oil to improve lubricant performance under a wide variety of operating conditions. Additive types may include viscosity modifiers to help maintain lubricant viscosity grade despite wide fluctuations in operating temperatures. Generally, viscosity modifiers are oil-soluble organic polymers which thicken oil relatively more at high temperatures than at low. At low temperatures, where high viscosity is undesirable, the polymer molecules occupy a small volume and have minimal association with the bulk oil. At high temperatures, the polymer chains expand. This increases the polymer's association with the bulk oil due to expanded surface area. The effect is to increase the viscosity. Viscosity modifiers extend the temperature range over which a lubricant can function effectively, an important feature for fluids that must operate in all seasons. Detergents prevent contaminants from accumulating on component surfaces and also neutralize the corrosive effects of combustion or oxidation products. For example, they protect against sulfur acids formed during the combustion of diesel and marine fuels containing sulfur. Detergents, primarily metallic salts such as calcium, magnesium, or sodium of organic acids, are used mainly in engine oils and metalworking fluids, with some use in transmission fluids and greases. Detergents protect parts against carbon and varnish buildup, which is vital for parts with close clearance, such as piston rings and skirts, valve lifters, and oil pump relief valves. Dispersants minimize the tendency of contaminants to agglomerate into large lumps, which settle out as sludge or varnish. Although both dispersants and detergents act as cleanliness agents, they differ chemically. Dispersants are non-metallic materials and are more effective than metallic detergents in controlling engine deposits under intermittent or low-temperature operations. Anti-wear agents reduce the loss of metal from component surfaces by preventing metal-to-metal contact under high loads. They include film-forming compounds like zinc dithiophosphates, which protect by reacting with or adsorbing onto metal surfaces. Extreme pressure agents are a special type of anti-wear component for use under extreme loads, low speed and high temperature. They react with asperities on surfaces to reduce friction and wear. These chemicals are especially useful in gear lubricants, greases, metalworking fluids, and other applications where high loads are common. Antioxidants minimize lubricant thickening and degradation caused when oxygen reacts with the churning lubricant at high temperatures in engines, transmissions, and gearboxes. As a rule of thumb, for every 10 degrees centigrade increase in operating temperature, the oxidation rate of an unprotected lubricant almost doubles. Antioxidants work by either reacting with unstable oxidation products or by decomposing peroxides in the oil. Oil thickened by oxidation can cause bearing failure if the oil pump cannot maintain a sufficient flow, and it can even prevent an engine from starting. Oxidized oil also contains acids which can corrode metal surfaces. Inhibitors are needed to protect against rust and corrosion caused by the attack of oxygen and acidic byproducts on metal surfaces. Normally, the rust and corrosion rate is low, but it increases greatly when unprotected metal is in the presence of water and oxygen. Unfortunately, these elements are present in abundance in internal combustion engines. Rusting, the oxidation of iron, can cause frozen hydraulic lifters and stuck oil pressure relief valves. And it can actually destroy engines, transmissions, the final drive gears, and bearings. By forming a protective film on metal surfaces, rust inhibitors provide a barrier between the metal and the rust-causing moisture and oxygen. Anti-foam agents eliminate lubricant foaming caused when the churning action of mechanical parts creates bubbles by mixing the oil with air. Excessive foaming reduces lubricant effectiveness by disturbing the hydrodynamic film between meshing parts. Foam inhibitors prevent this problem by decreasing the surface tension of the lubricant and allowing the air to escape. Pour-point depressants control paraffinic wax crystal formation at low temperatures by interrupting crystal growth and are especially useful in lubricating oil and fuels. Reducing crystal size and altering their shape maintains proper lubricant viscosity and flow, important for sub-zero startup capabilities.
It came out of the ground as crude. Then it was refined and analyzed. An additive package was developed to provide the physical and chemical properties needed to meet the prescribed performance level. And then the formulation was subjected to a complete series of engine tests to document performance against the targeted industry specifications. Careful selection, painstaking formulation, rigorous testing. These ingredients in the lubricant are the source of consumer confidence.